You're familiar with the real number line, I hope. It extends to infinity in both directions. We can't really handle that in a computer, but it actually turns out to be not much of a problem, so we don't worry about it. The more interesting problem is turning the continuum of real numbers into a discrete set, which we need to do if we're going to take a finite amount of time. So we have this function fl, which maps each real number x to its floating point counterpart. And you always choose the nearest possible floating point representative, which is very close by in the sense that the distance scales like 10 to the minus 16 for this number epsilon. One interpretation is that the potential distance between floating point numbers scales with the size of x itself, or another interpretation is that the relative difference between x and its floating point representative is this number epsilon, which is bounded by the small number epsilon sub m. The same statements are true about things like multiplication, addition, and so on. They're all relatively accurate. Now, you're probably familiar with the concept of significant digits from laboratory science. So if x is 6.02 times 10 to the 23rd, but the last digit is uncertain, let's say we just change that last digit and call it x tilde. Then the relative distance between the two is the ratio of 0.01 and the original x. Both of them are scaled by that 10 to the 23rd, which cancels out. And the answer is 1 part in 602. So it's the same result whether you have this number or 0.602 or something with a very small scale. They all have what we would call 3 significant digits or 3 digits. Now in computing, all the numbers that you get have 16 significant digits because epsilon sub m is about 10 to the minus 16. But it's important to realize that not all those digits are necessarily accurate for the problem you're trying to solve. Finally, there's an important implication for equality in floating point numbers. So the question, is x equal to y, is a pretty tough one to solve if x and y are arrived at by different operations with lots of round off in them. So even if they should be the same, they probably won't be identical. So it's better and more robust to ask the question, is the difference between x and y small? And of course, we have to say exactly what we mean by small, and that should be relative to the size of the original x and y themselves for some number delta.